Hello, I'm Ryota Gomi from Tohoku University, Japan. I'm going to talk about InflattableBots, which are inflatable shape-changing mobile robots for large-scale encounter that haptics in VR. Large-scale haptics have a lot of potential for completely immersive VR experiences. Large-scale encounter that haptics enables users to connect with haptically rendered VR environments through body-scale interactions, such as walking around and pushing virtual objects, just as they are interacting with them in the physical space. Inflatable-based haptics come out as a promising approach, as they allow for safe, low-cost, and robust haptic interactions. However, the existing large-scale inflatable structure have a key limitation in scalability and deployability. Encounter-type haptics provides haptic feeling by dynamically adjusting the touch point with the object position upon user contact. This approach enables a large interaction area and easy to deploy. We aim to move to larger scale by using inflatable actuation and encounter-type mobile robot. We propose InflattableBots. InflattableBots is a modular robot system combining mobile robots with inflatable shape-changing structures. The inflatable structures provide dynamic height-changing abilities. We developed 3 shape-changing inflatable mobile robots that can use in a large walkable space. Here is an overview of InflattableBot configuration: vinyl tube, baseplate, and mobile actuator. The system employs a vinyl tube which is stored in a spool format at the center of the base. This spool design allows a height change spanning from 40 cm to 200 cm with a compact base dimension of 25 cm diameter circle. The fan-based inflation mechanism allows fast and dynamic shape changing with a speed of 10.4 cm per second. We present several haptic interaction techniques enabled by InflattableBots. By taking advantage both mobility and shape-changing ability, InflattableBots enable unique and expressive haptic interactions. Interacting with multiple stationary, interacting with moving objects, interacting with continuous surface, interacting with shape-changing objects, and interacting with objects through handheld tool. The video shows interacting with multiple stationary. Interacting with moving objects. Interacting with continuous surface. Interacting with shape-changing objects. And interacting with objects through handheld tools. We propose a set of application scenarios that take advantage of the unique feature of InflattableBots. The video shows playing sports and walking in a large space. We conducted a user study to understand the user experiences with InflattableBots. InflattableBots have many factors, with the goal of this study is to test the fundamental questions regarding InflattableBots' haptic rendering ability and its system operation in room-scale VR experiences. The user study was designed to evaluate InflattableBots' haptic rendering ability, geometric rendering ability, and user experience with InflattableBots through 3 design tasks. Task 1 was designed to evaluate the reality of InflattableBots haptic rendering for different shapes, hardness, and surface textures of objects. We compared 6 types of objects under the 3 haptic conditions: mid-wear, one tooth, then use of InflattableBots. They then answered the question about reality on the Richter scale from 1 to 7. The video now shows each condition: mid-wear, ground truth, and InflattableBots. This shows an overview of the results. For all objects, the scores in both InflattableBots and the ground truth condition were significantly higher than in the mid-wear condition, and the ground truth score was significantly higher than the InflattableBot score. These results suggest that the soft physical feedback of the InflattableBots offers some advantage for haptic representation, but does not reach a realistic touch experience. Factors specifically mentioned in the interview were surface hardness, shapes, and texture. In Task 2, we evaluated how whether InflattableBot represents continuous surface at different angles. We prepared 5 angles: 0, 15, 30, 50, and 70 degrees under 2 haptic conditions: InflattableBots and an actual inclined board as ground truth. This video now shows ground truth condition and InflattableBots condition. After each angle, participants answered 2 questions. The first question about the surface continuous regarding ability on Richter scale from 1 to 7. In the second question, participants estimate the angles. Several inclined board options were displayed in the VR, and they selected the one closest to what they experienced. This shows an overview of the results. The A shows the continuity score, and B shows the error degree of the tilt estimation. For all angles, the continuity score and the ground truth condition were significantly higher than the InflattableBots condition. Only for 30 degrees, the error was significantly larger under the InflattableBots condition than the ground truth condition. According to the interview, one reason that the InflattableBots condition scored lower than the ground truth was that the real slope has an incline on the upper surface, but the top of InflattableBots is almost flat. In Task 3, we evaluated the user experience by getting user feedback through application scenarios with InflattableBots. For this purpose, we implemented an application with 4 experiences, all themed around the farm. All experiences use different features of the InflattableBots. Participants experience the application in the order of a plant, a horse, dogs, and a pile. In this presentation, I'll report the questions regarding its experience in terms of preference and how helpful InflattableBot is in understanding the content from 1 to 7 Likert scale. A shows the score for preference, and B shows the score for understanding the content. We receive positive feedback that they could touch one dog and immediately touch the other without waiting time. Furthermore, the touch through the controller was that the influence of different texture was decreased. However, unless there is a match in hardness, shape, and texture, its effect is limited. And in horse touching, the InflattableBots move to follow the participant hands, and some point out noticeable delay or waiting time for the robot to arrive at the hand position. Finally, I report limitation and future work. Haptic rendering. As the study results showed, we acknowledge that the current InflattableBot type is ineffective in rendering various type haptic materials. One solution is to focus on the issue of the shape and texture of the top, and we could consider changing the physical properties of the top part. Stability. We could consider using more rigid vinyl materials and an air compressor system to create a more solid height-changing cylinder. Such stable inflatable prop could support physically item delivery through both interactions, such as sitting and leaning, or force representation in VR. Implementation improvement. To decrease positioning error, the next revision will add a rotary sensor to achieve a feedback loop system that can provide stable and accurate height control. In this work, we presented InflattableBots, shape-changing inflatable robots designed to enhance large-scale encounter-type haptic experiences in VR. Our approach combines the mobile robots with a fan-based inflatable structure. We report its design, implementation, and interaction techniques. We also show several types of user study and application showcase that demonstrate the benefit of InflattableBots. Thank you for listening.